In this series, we explain core Linux fundamentals like networking, namespaces, storage, permissions, and automation. But today, most DevOps workloads run inside container instead directly running on Linux. So in this final project video, we are going to build a small Linux container environment using a Linux commands. So there is no Docker, no Kubernetes, just a Linux kernel features. And by the end of this video, you will understand what a container really is and what actually happens behind the scene when Docker starts the run. Before we start typing commands, let's quickly understand what's actually happening behind the scenes when we run a container. Here at the top we have our container, that is container A and container B. At first glance, containers look like a small virtual machine, but in reality they are much simpler than that. Each container is just a process running on the same Linux system, and what makes them feel like a separate machine is something called namespaces. Linux provides different types of namespaces to isolate parts of the system. So let's have a look on that. So first we have a PID namespace that isolates the process list. Then we have a network namespace. It gives each container its own network stack. Then we have a mount namespace. It isolates the file system view. And at last we have a UTS namespace, which allows each container to have its own host name. So even though these containers run on the same machine, each one sees its own isolated version of the system. And all of this isolation is implemented directly by the Linux kernel. And the kernel is responsible for creating and managing these namespaces. And this is where Docker comes in. Docker doesn't actually create containers by itself. Instead, it simply automates the creation and management of these kernel features. So instead of using Docker today, we are going to create these namespaces manually using the Linux command. So containers begin by creating isolated namespaces inside the Linux kernel. So let's start a demo with multiple namespaces isolated. So this is our Linux machine. So now let's create a container using an unshare command. So for that we can use unshare --pid --uts -net -mount and -fork and -mount -proc and the bash. So this command might look complex as of now, but each option enables a different type of isolation. So let me explain it very quickly. So here -pid creates a new process namespace, and the processes inside this environment will see their own process tree. Then we are using the -uts, that is a UTS namespace. This allows the container to have its own host name. Then we are using -net, that is used to create a completely separate network stack. And after that I am using -mount, that means file system mount can be isolated as well. And after that I am using -fork, that means it runs our shell as a first process in the new namespace. And at last I am using the -mount -proc. So this mounts the /proc file system, so the new process namespace work correctly. And I am giving a bash shell to this particular container as well, so that's why I am using bash here. So let's press enter here. So at this point we are now inside a container like environment. So let's see what processes exist inside this environment. So for that we can use echo $. The variable $$ prints the process ID of the current shell. So let's press enter here. So as you can see, we got a PID 1. So inside this namespace, our shell has become a PID 1. So now let's see what processes are running inside this particular environment. So if I run ps-ef, so you will notice that only a few processes are visible. This is exactly how containers work. Every container has its own PID 1, which becomes the main process of the container. And for us, this is a bash, because we are running a bash shell inside this particular container. And in Kubernetes as well, the container entry point becomes the PID 1 only. So container also need their own system identity, and this is controlled by the UTS namespace, which manages hostname. So as of now, if I run hostname, so this shows the current hostname inside this environment. So let's change this as well. So if I run hostname devops -container, so the hostname got changed, and if I run hostname command again, we can see the hostname got changed to devops -container. The hostname has been changed only inside this particular container only, but on the host systems, hostname remains unchanged. This is why containers feels like a separate machines, even though they run on the same host. So if we want to see the kernel namespace object in this particular container, we can see the /proc file system, which we have mounted using the -mount -proc option. So Linux exposes namespace information through the /proc file system only. So if I run ls-l/proc and $, which is a current process ID, and then the ns. So what you are seeing here are symbolic links. Each link represents a namespace attached to these processes. So the number inside the square brackets is the kernel identifier for that namespace instance, and the processes that share the same namespace ID are in the same isolated environment. Now let's look at the most important namespace used by the container. So first of all, we have a PID namespace that controls process visibility. So processes inside a container can only see processes inside that namespace only. Then we have a network namespace that provides an isolated network stack. So each container gets its own interfaces, routing tables, and the firewall rules. Then we have a mount namespace that controls file system mount points. This is how containers get their own file system. And we have a UTS namespace as well that controls hostname and the domain name. And this is why container can have their own hostname. And this is why container feels like a separate machines even though they run on the same host. And the same thing which we have done using the hostname command. We change the hostname inside this particular container, but the host system hostname will remain unchanged. So the container runtimes like Docker, Containerd, or even Podname don't invent isolation. They simply create and manage these namespaces automatically. So every container is really just a process attached to its own set of namespaces. So far we have isolated the process and the host name, but containers also start with something else isolated, that is networking. So let's see what networking looks like inside this environment. So for that, if I run ip-addr command, so you will notice something interesting here. Only the loopback interface exists, and there are no Ethernet interfaces, and there are no external IP addresses as well. This means this environment currently has no network connectivity to the outside world. So when the container runtimes create the containers, they solve this automatically using networking plugins. In Kubernetes, this is handled by CNI plugins like Calico or Flannel, but under the hood, they are doing something very similar to what we are about to do manually. So let's build the container networking ourselves. So to connect this container to a network, we first need a virtual cable. In Linux, that cable is called a VETH pair. The VETH pair looks like a virtual Ethernet cable, and anything sent on one end appears on the other end as well. So for that, we need to go to the host system. So let me duplicate the session here and let me enter the password. So let me change the names here as well. This is the host system and this is our container. So now I'm going to create a VETH pair on the host system side. And if I run hostname command here, and we can see the host system hostname remains unchanged. So we have changed the container hostname to devops-container, but the host system hostname is master01 only. So that means this particular environment is working just like a container only. So now let's create a VETH pair here. For that I can use IP link add VETH-host type VETH pair name and VETH-container. So let me explain this command very quickly. So IP link command manages network interfaces, and I'm going to create a new interface. For that I am using a add option, and after that I am giving a VETH-host. That is the name of the first interface, and here I am specifying the type, that is VETH, that creates a virtual Ethernet pair, and after that I am specifying the pair name, that is the name of the connected interface. So this command creates two connected interfaces. So let's press enter here. So the two connected interfaces got created. So let's run ip-addr command here. So we can see VETH-con and VETH-host has been created, and one side remain on the host and the other side will move to the container. So to move it, we first need the container process ID. So for that we can run ps-ef and grep for unshare. Unshare, because we have used the unshare command to create a container. So here we can see this is the process ID, that is 9947. So this process ID represents the process running inside our isolated namespace, and now we can move the network interface into that namespace. So for that we can run IP link set VETH-cont and netns and the process ID, that is 9947. So let me explain it very quickly. So IP link set means modify the network interface, that is VETH-cont, which we have created earlier, and then I am specifying that move the interface into the network namespace of process, that is 9947. So let's press enter. So in Linux, each process can have its own network namespace. So this command moves the interface into that namespace. So now if I run ip-addr, we can see the VETH-cont has been removed from here. And let's go back to the container, and if I run the same command again. So now the container have received one end of the virtual cable, which we just did using the IP link set command. Next we need to configure the host side of the connection. So for that we need to assign the IP address to the VETH-host. So for that we can run IP addr add and the IP address subnet, that is 10.0.0.1/24, and dev and VETH -host, that is hyphen. So IP addr add means assign an IP address, and here I am providing the IP address and the subnet mask. And here I am specifying the interface as well. So this gives the host side interface and IP address. So let's press enter. And if I run the same command again, that is IP addr. So if you see earlier, there was no IP. And as soon as I press enter, so as we can see, the IP address got added to the interface. So right now this interface is down because the new interface starts in a down state. So let's bring it up. So for that we can run IP link set and the interface name, that is VETH host, and the up option. So if I run IP addr command again, so now the VETH host interface is up. So now it can send and receive a traffic. So it's time to configure the container side of interface as well. So let's go back to the container, and here we need to assign the IP address as well. So for that I can run IP addr add 10.0.0.2 and 24. And the container interface, that is VETH -cont. So this assigns an IP address to the container interface as well, and that is hyphen, and let's press enter. And if I run IP addr, so here we can see the IP address got attached to the container interface as well, but this one is also down by default. So let's bring it up as well. So IP link set VETH -cont and up. So this activates the container network interface as well, and we need to bring up the loopback interface as well. As you can see, it's also down. So if I run the same command with the loopback interface, that is LO. So now the loopback interface also enabled, so local networking works properly. And if I run IP addr, so now we can see the loopback interface is up and running, and the container network interface also has an IP address and it's also up. Now let's test if the connection actually works or not. So for that we can ping the host IP address, that is ping -c3 and 10.0.0.1. That is the IP address which we have assigned to the host side interface. So as we can see, it's able to ping to that particular IP address. So basically ping sends an ICMP packets to test the network connectivity. So if the packet returns successfully, it means the connection is working. And we can see packet returns successfully, and this confirms the container can now communicate with the host. So when Docker or Kubernetes creates a container, they automatically create these VETH pairs and connect them to container bridges. So what we just did manually is exactly what container runtimes automate. And if we try to reach to this particular container as well from our host, we can try to do the ping from the host as well to the container IP address, that is ping -c3 and 10.0.0.2. And we can see we are able to connect to the container as well. But container isolate more than networking. They isolate file system as well. So container uses mount namespace to isolate file system mounts. And this allows a container to mount file system without affecting the host. So let's create a directory inside the container first. So let's go back to the container and run mkdir/mnt and /data. So we will use this directory as a mount PID inside the container. So as we can see, this particular directory is already created. Let's mount this to a tmpfs. So for that we can use mount-t tmpfs and mnt/data. So here the mount attaches the file system, and -t tmpfs specifies the file system type, that is tmpfs, and here we are specifying the mount location, that is /mnt/data. So tmpfs stores file entirely in RAM instead of disk. So any file written here disappear when the container stops. And let's press enter. And if I run mount and grep for data, we can see the output here. That is tmpfs is mounted on /mnt/data, and the type is tmpfs only. And if I run tf-h to see the disk usage, so here as well we can see the tmpfs is mounted on /mnt/data, and it's having a size that is 7 GB. So far we explore how container isolate processes, networking, and even file system. We have also mounted temporary file system inside the container using tmpfs, And in real container platforms, runtimes like Docker usually uses overlayfs to build a container file system. And don't worry, we are going to cover the overlayfs in the upcoming videos, but container really run in isolation. In real system, container constantly communicate with other services. So let's simulate a very common DevOps task, debugging a connectivity between a container and the services. So to demonstrate this, we will start a simple HTTP service on the host machine. So let's go back to the host machine, and here I am going to run a lightweight web server using Python. So for that I am going to use a Python 3-m http.server and port number that is 8080. So this command starts a lightweight web server using a Python, and it serves the files from the current directory on port number 8080. Now let's see our container can reach to this service or not. Let's press enter. So as we can see, this web server got started on port number 8080. Now go back to our container and let's try to connect to this particular service. For that we can use curl http and the IP address of the host, that is 10.0.0.1, and the port number, that is 8080. So here we are using a curl to send a HTTP request to the host and on port number 8080. And if I press enter, and we are able to access our web service, and here it shows the directory listing from the slash drive. And if we come back to the host, and here we can see the traffic came from 10.0.0.2, that is a container IP address on this particular date and the timing, and the connection got established and we got a 200 response. That means our container are able to connect to the service which is running on the host. And this is exactly the kind of test engineers run when debugging connectivity issues inside the Kubernetes pod. So we have now manually built many of the core building blocks behind the containers. So let's exit this particular container. For that we can run exit command, and if I run echo $, we can see it shows a different process ID. That means we are not inside the container. And now we are back on the host system. So everything we created, that is namespaces, networking, and file system isolation, is exactly what container runtimes automate every time you start a container. What we have built today is essentially a container, but there is no Docker, no Kubernetes, just a Linux kernel primitives. Containers are built using a few Linux fundamental features like namespaces, process isolation, virtual networking, and file system isolation. And real container also uses cgroup to control memory and the CPU usage that we are going to explore in the upcoming videos. So Docker doesn't create container, but Linux does. Docker simply automates the thing which we have done in this particular video using the Linux commands. And DevOps is not about knowing commands, it's about understanding the system behind them. If you found this video helpful, hit like, share it with your friends, and subscribe for more content like this. If you want to learn more about Linux internals like cgroups, overlayfs, and container security, subscribe and turn on the bell icon so you won't miss the notification about the upcoming videos.